Good morning, everybody. Welcome to today's machinery safety webinar from Pilz. My name's Jamie Thomas and I'll be your presenter. I have my colleagues Alex Bryce and Jason Reed supporting me today, answering your questions. So you can use the questions facility in the toolbar to the right hand side of your screen if you've got any questions you want answering live today. A link to the webinar will be sent out on the completion and probably today or Monday, and a copy of the slides is available upon request. So yeah, just let me know if you can hear me okay, that would be great. So today, the things we're going to cover, we're going to briefly go over functional safety and what it is. And we're going to run through some key parts of 13849 Part 1. Some of the changes from the latest version of 2023. We shan't be going through the whole standard. It is a big, complex standard, and we'd be here all day. So we're just going to go through some of the more key areas. So what is functional safety? It's the part of the safety system. It's often referred to as safety-related parts of the control system. So you may see the abbreviation SRPCS. And it's designed and implemented to reduce risk. And the aim or the function is generally to establish a safe state and avoid, where possible, contact with hazardous parts of the moving machine, and it's to be operated in an emergency. Some of the functions may be modes or to allow people to do things at slow speed, so it doesn't necessarily always mean everything has to come to a standstill, but some of these safe modes will be implemented also through the safety-related parts of the control system. But the intention of the safety-related control system is not only to limit risk via control, but also to avoid any systematic or random faults and the reaction to faults which arise from the hardware or software and any mechanical elements. So the main standards referred to in functional safety are 13849 and 62061. We'll predominantly be concentrating on 13849 today. Both are harmonised to the Machinery Directive or designated to the Supply of Machinery Safety Regulations, whichever way you want to go, whichever way you're looking at it. And they're both vital to the design of the safety-related control systems for machinery. And systems are referred directly by many of the B and C standards. So therefore OEMs and SIs, they are a key part to what they do in their design. 13849 itself is a B standard, and for those that don't know, C standards are machine specific standards. So maybe an example where you would hear this referred to would be in the robotics standard 10218 Part 2, where it will say that safety functions need to meet a minimum of performance level D category 3. So you can see there a direct reference to 13849. A little while ago, there was a project to attempt to merge these standards and create a standard called IEC ISO 7305. However, this failed due to some formal reasons. So both standards went their separate ways and into their maintenance and review cycles, leading to the latest updates and versions that you'll see in the webinar later today. But you can also see from them conversations, there was a lot of, you will notice there was a lot of commonality in the changes that were made. So 13849 Part 1, Functional Safety. This is the structure of the standard, so it goes through, so it's sort of scope, what it covers, any of the normative references, gives you information in section 3 on any of the terms and symbols, abbreviations, so when you're reading through you can understand what's meant. You've got an overview. You've got specifications of safety functions, design considerations, any software safety requirements, because obviously through the years of revisions from 954 through to early versions of 13849 from 2006 onwards, software has become a bigger part in machine safety. How you can verify that you achieve your performance level, any ergonomic aspects of design. But then one of the big changes here is section 10. So validation has been included. So all the normative parts of 13849 part 2 2012 have been put into section 10. So that's a new part. And then it comes on to maintainability, technical documentation, and information for use with the annexes. So we'll just have a quick recap here on the approach which should be applied to all safety related applications. The first stage, the top 3 sort of beigey coloured items are around your risk assessment, and all machinery safety applications should start with a risk assessment. The key parts which are going to be covered from 13849 come below, so we're going to go through the risk reduction. So again, the first stage from the hierarchy of control is risk reduction by inherently safe design. So before you go to the options of guarding and adding safety related control systems, you must always see if you can design that hazard out. And that is the ideal scenario, and that's what you must look at to start with. When you can't, then you'll go through and create your safe solution, whether that be by guarding or safe related control system. So you'll come down, you'll identify your safety functions in your safety requirement specification. You determine the performance level, or still, but we'll generally be talking performance level today, for the safety function. Then you'll go through your design, selection of architectures and components, and then you'll look at the evaluation and verification of the expected performance. So will that design, before you get into the design, will what you propose to design meet the performance level? Then you'll go through your installation and your commissioning of your safety related control system, and then we'll come to the validation, what you need to do, and that again, that's the parts of section 10. We won't go into massive detail on that because again, it's a big topic all in itself. And then once you've done that, you'll go through this sort of iterative process of your safety system. There's guidance given in section 4, and this is the methodology from section 4.4 of what you would do with a safety related control system. So when you determine that you haven't been able to design the hazard out and your risk reduction is going to require a safety function, if you can see on the right, if it doesn't, then you can jump straight down and see if your risk is suitable. If it's guarding, you'll safeguarding, you'll go off to the left. So if we're going to go down the center, which is what we're looking at for safety related control systems, you have to specify the function and determine the performance level. And we'll come on to how we determine them performance levels in the next slide. So you design your safety related control system to perform the required safety function. For the performance level, we're going to look at the category of architecture, the mean time to dangerous failure, what diagnostic coverage it can achieve, are there any systematic failures, are the basic safety principles been applied, and then when we're looking at, if applicable, when we're looking at components, we've got well-tried safety principles, well-tried components, and any requirements if we're going to use a software-based solution. So then we go down, further down, we go through the verification, which is often confused with validation. Verification is the calculation, and the validation is the physical testing of the system with fault injections, etc. At any of these points, if you fail, you have to go back up to the top and restart the process. So it is an iterative process for the design, and you have to keep analysing and going around. And at any point you deem that you've fallen short, you go back to the top and restart the process. So as we said, we've got to determine the performance level. And this is done by a few factors that we'll run through now, and they are severity of injury, frequency of exposure to the hazard, and the possibility of avoiding or limiting harm. So the first one is severity of injury. We have S1, which is slight, S2, which is serious. The point in which you can make that differentiation generally is broken fingers, broken toes are seen as slight, metatarsal, metacarpal is seen as serious, and anything for any broken bones further up the body from there are classed as serious or irreversible. If you've got a cut that you can put a plaster on, or a burn that you can treat with just water on site, then generally you would be in the area of slight. If you've got to go to hospital for any of these injuries and they require days off work, then you would be in the serious or S2 category. Frequency of exposure. So with this, a key part to remember is you assume high unless you can prove otherwise. So you must prove that you are in F1. If you can't, you will be in F2. And the parameters for this are more frequently than, or less frequently than once every 15 minutes, or 1/20th of the machine's overall operating time accumulatively. So that would be 24 minutes in an 8-hour shift. So if you are accumulatively, easy for me to say, exposed to this hazard for more than 24 minutes, that could be in one single exposure time or a number of smaller exposure times, then you have to prove that you are less than that to go down the F1, otherwise you will assume F2. And then the possibility of avoiding the hazard is possible under specific conditions or scarcely possible. We'll come on to some more detail in this because there's more guidance given in the 2023 version of 13849 on how to justify this. Again, if we reference 10.218 part 2, they give you as a C-type standard, they give you a specific value. They say if the robot is moving at less than 250 millimeters per second, then you can claim avoidance. Funnily enough, the maximum teach speed of a robot is 250 millimeters per second because you'll need to be in the cell with the robot generally to teach it, so, or quite often. So that's why they've given that value. To achieve the performance level, there are a number of factors. So the total probability of failure is not attributed to just one part of the system, and all these factors need to be considered. And this slide basically demonstrates the chance of a dangerous failure is not only based on the reliability of one component, but it depends upon the total loop. And all of the parameters which we design are effective on the total calculation, and it depends on the whole structure. So this can be useful when discussing potential failures at the design stage with your designers and engineers, and when you're talking about which parameters are to be affected with the total failure. So we have diagnostic coverage. So this is the system's ability to diagnose dangerous failures upon itself. We have common cause failures, so we don't want a single failure leading to multiple failures. Reliability of the components, the category of architecture, so we have 5 of them, and again we'll come on to these a bit more, and any systematic failures. But you'll see that the reliability and the diagnostic coverage and things like that that are coming in, these were fairly new to 13849 back when it was born and taken over from 954. So 954 was an architectural based standard which just looked at these categories, B, 1, 2, 3, 4, and they've been maintained through the life cycle of 13849. But 13849 is a reliability based standard, so it pulls together the good parts from 954 and adds to it as a standard. So what is diagnostic coverage? As I said before, it's the system's ability or the subsystem's ability to detect dangerous failures upon itself and do something about it. And that something is usually to establish a fail-safe condition. It's expressed as a percentage, and the way the calculation is determined, it is the sum of all failure rates of detected dangerous failures over the sum of the rates of all total dangerous failures. So your system, to claim any diagnostic coverage, must be able to detect upon itself 60% of all dangerous failures. If you can't, you cannot claim any diagnostic coverage, and there's implications to that which we'll look at later. If you can detect between 60 and 90, then you have low diagnostic coverage. 90 to 99 is medium, and if you are then going to claim that you're going to detect all dangerous failures and the system's going to detect them either immediately or for the next demand upon the safety function, you can claim high diagnostic coverage. As we talked earlier about references to from other B standards, so when 14119 took over from 1088 as the interlocking standard, there was a reference in there in the technical report TR24119, which supported the standard, to state that actually if there's a table in there which talks about open guards, and there was a line underneath that said something like if it's foreseeable that fault masking will occur, i.e. multiple movable guards could be open at the same time for general use or service, then diagnostic coverage would be limited to none. So for that specific part of a safe flight control system, it referenced 13849 and made a statement about what diagnostic coverage you could claim for your interlocking architecture. So that's where everybody went away from series linking fault-free contacts. But we digress, and we'll carry on. The category of circuits. So we have 5 here. Category B, and then 1, 2, 3, and 4. And these, as I say, were taken from previous standard 954. Category B is a very basic circuit. That's what B stands for. Single channel, no diagnostic coverage, but the MTTFD of the components in this case are low. So they're not classed as well-tried components. The maximum performance level you can achieve with this type of architecture and these components would be performance level B. Category 1 is the same as category B in the way that it's single channel, no diagnostic coverage. However, in this case, we would have a high MTTFD of the products or the components, and therefore we can achieve performance level C. We show input logic and output device in this architecture. It is possible with well-tried components to achieve performance level C without a logic device. So an e-stop could be directly breaking the power to a contactor coil and actually achieve performance level C. Is that recommended? Probably not, but it is possible. Category 2. So this it has redundancy, but not in the true sense of the word as we would look at in the next 2. What it does, it has a single channel which is always operating, and So you've got your input device, your logic device, and your output device. You have a low to medium diagnostic coverage, and this is done by monitoring the feedback from your primary contactor. And what your logic device will do in this case is detect a failure of that primary contactor. So if that welds in and we don't see the feedback signal come back on the de-energization from the logic device, a decision or reaction will be made within the logic device to say, I've detected a failure, I now need to remove the power to an upstream mainline contactor. So, and this is via what's classed as your test channel. So you do have redundancy in the way of an upstream contactor, but it's not operating upon every operation of the safety function, only when it detects a failure. And we've modeled this architecture with a light curtain in the graphic, because as many of you may know, when you're doing stop performance tests for electrosensitive protective equipment, or light curtains, some of them are better known, you'll do your 13855 calculation of S equals K times T plus C, and with T1 and T2 being the values which make up your overall reaction time and mechanical stopping time of the safe control system. To correctly position these light curtains, you must always take your worst case scenario. So that must be in the case of a failure where the primary contactor has failed, the reaction time of the safety logic device making the decision to shut off the upstream mainline contactor to bring the machine to a standstill. So that would be how you would have to do the calculation to determine the safe distance for your light curtains or floor scanners, whichever you were going to use. Category 3 architecture. So you can have from low to high MTTFDs of these products. It's a redundant architecture where you have 2 channels, and we do have cross monitoring between a lot of these channels. We have 2 shutdown output devices in this. However, we don't have, we cannot detect all dangerous failures, and you can see from the dotted line between the logic device to the output device, that means it's reasonably foreseeable detectable failures. We're not going to detect all failures. Therefore, the maximum you can generally achieve with this is performance level D. And this is where you would come in, obviously, sort of PLD Cat 3 with other specifications. The difference between category 4 architecture and category 3 is that you can see the two-way directional arrow M is solid. So what we're doing there, we're now monitoring the failures in both directions, and we're detecting all failures between the logic device and the output device. We've got solid line between the 2 channels as well, which means we're going to detect all failures between them 2 channels for the short circuit detection or single channel failures, whatever it may be. To achieve this, then we could claim a high diagnostic coverage. So we are going to, as I say, going to detect above 99% of all failures, and we have a high MTTFD of all our products. So this is what's required to achieve performance level E with a category 4 architecture, high MTTFDs and high diagnostic coverage. So for the estimation of a mean time to dangerous failure of a component, there is an order of priority which will be followed. If available, we use the manufacturer's data. So if they produce and publish that data, then that is the best way to determine the mean time to dangerous failure of the product. One thing to just be aware of is that if a manufacturer does publish this data, it will be based on a number of operations. And and you've got to make sure that you're not going to exceed this. So if a door's being opened frequently, a contactor's going in and out very frequently, then actually you might exceed the data which it's stated, and therefore that could reduce your MTTFD. You can use methods in Annex C for good engineering practice as well. So if you're looking at things, well-tried principles, component manufacturers, operating conditions of the safe-related parts control system, and well-tried safety principles for the design of the safe-related parts control system. And you'll do this in accordance with 13849 Part 2. Another option, third option, would be failure rate data from identical components in applications in similar environments. And these could be collected over, they'd have to be collected over a significant period of time, and where the collection and analysis methods results in a reasonable level of confidence in the data. So you'd have to be from a reliable source. You're going to have to then sort of refer back then to the sort of daddy standard of machinery safety, which is 61508, and that's how you would look at that. If you can't claim any or use any of this data, I can't find the published data, then you could just choose 10 years. Expected life cycle of a machine is generally 20, so it's erring on the side of caution. But you do this by referring to what was table 5. As you can see here, it's table 6 in the latest version of the standard. And you can see that the maximum MTTFD for each channel is limited. So the highest MTTFD is limited to 100 years. There is an exception to this, and this is for category 4 architectures, where you're going to be claiming high diagnostic coverage and you've got all that good stuff. And this capping is increased to 2,500 years. The reason for that was that in previous versions of 13849, everything was capped to 100 years, and this was actually changed in 2015, but so it's not new to 2023, but you would find that there was an accumulative effect in your verification where you would have various subsystems all capable of achieving performance level E, but the overall architecture was dropping down to D just due to the accumulative effect. So this wasn't deemed to be fair or accurate. So this capping was increased for very specific requirements where you have PLE Cat 4 devices or systems. You've also got to consider common cause failure. So this is table F1 from the standard, and what you've got to look at that is the probability of 2 or more separate faults having a common cause. So we don't want one issue causing multiple failures. And there's a scoring system which we'd use for this. So you go through and answer the questions. So there's further questions around these. So you've got to look at separation and segregation, diversity. Can you do pressure and flow in a system or something like that, or differing devices of the same type from different manufacturers potentially, if they're not safety rated. When you look at the design, so have you protect against over voltage or over pressure, over current, over temperature? We come back to the components being used are well tried, so they have higher MTTFDs. Have you done due diligence with your assessment, your analysis? Is the engineer trained? Is he trained in safety-related control systems or experienced in machinery safety? There's environmental considerations. So is the are the components or the systems being used suitable for the environment that they're being installed in? So you've got to go through all these, and you would need to achieve a score of 65 or better to be able to meet the requirements for common cause failure. So this graph here is figure 5 out of the standard, and it's just a rough estimate of that you can use at the design phase to see, right, okay, what performance level what is my target performance level, and what do I need out of my system to be able to achieve that. So you can see from the colours that dictate the MTTFDs, and the position of them is whether it's got what the category circuit is and whether it's got diagnostic coverage or not. And you can see it is possible with a Cat3 architecture and high MTTFD and medium diagnostic coverage to achieve performance level E. But generally, if you're going to go for that, it would be Cat4 with high diagnostic coverage. And this, like I say, this is it's just intended to be a quick evaluation. The detail is actually in table K1 taken from Annex K of 13849. And this is where you have all your PFHD values. So this is what the targets are to an order of magnitude. And you can see how the performance level changes with that order of magnitude. As we said earlier, how diagnostic coverage can have an effect on your system. No matter how you wire your system, people may have a 4-wire system and think they've got a category 4, at least a category 3 architecture. If you cannot claim diagnostic coverage, so maybe there's no feedback of the contactors, or you haven't got short circuit detection, or you've series linked fault-free contacts for the purpose of interlocking, therefore there's a probability of fault masking, you then can't claim any diagnostic coverage and you will revert to a category 1 architecture. And you'll see from that that the maximum performance level you can achieve then is C. So without any diagnostic coverage, that is the maximum you can achieve. So you've got to consider this in your design and understanding of safety-related control systems. So changes in the standards. There was some guidance given on the methodology for defining the required safety performance or SEAL level. Requirements for the application of software, depending upon the complexity and whichever programming language you were selecting, and the allowance of subsystems to be developed in accordance with one standard or another and then be used together. So this table just shows now that all the versions of 13849 and 62061 which have been in transition are now published, harmonized, designated, whichever way you want to call it, and they are now all available to use. There's a transition for 13849 from 2015 to 2023, which runs until the 15th of May 2027. At that point, the 2015 version will be withdrawn and can no longer be used. The idea of this transition, though, is not to start new projects using 2015. It's to allow the completion of existing projects. So if you're starting any new projects now, you should be looking at the requirements of 13849 Part 1 2023. And then looking at the upcoming changes and applying them to your project. So what are the changes? As we said, the validation parts of 13849 Part 2 have been put into section 10 of the new standard. So as it stands, part 2 is as was, no changes, still relevant, still live, and you reference that for your validation. However, these sections have been taken from that standard and put into section 10. So all the stuff on validation principles, validation of the safety requirement specification, validation by analysis, validation by testing. It's always good to point out that analysis does not substitute testing, it can only support it. Validation of safety functions, integrity of the safety related control system, environmental requirements, how you record your validation, and any maintenance requirements. So all that good stuff is now in section 10 of 13849 part 1. There's been a strong focus on the definition of safety functions within a safety requirement specification, and there are now a higher onus on what you put into your safety requirement specification. And this is something we often see missed or not done very well, in my experience, when we're looking at systems with people. So from now on, under 13.849/2023, you put each safety function, you are required to describe the function, and that includes any trigger events, what its reactions are, and what the safe state is. We've got to state the target performance level. If there's any related operating modes which are going to be used within the safety function, what its response times are, what its fault reaction and behavior is. So this is a key part. So how is it meant to, or designed or required to react in a fault condition? Does it have priority over other safety functions? And this will be key for emergency stops particularly. And how does it interface with any other safety functions? So to have a sort of a view on how this might look, I've given an example here for an e-stop. So we've got a description. So when the emergency stop is pushed, the button will lock itself, and the safety control system shall directly remove hazardous AC power to the conveyor motor, which is M1 in the drawing, by switching off the redundant supply contactors K1 and K2 and use the stop category 0. So stop category 0 is removal of power and the machine comes to a stop under its own volition. The safety function is always active in all modes of operation, whether that manual or automatic. And yes, that would be the case because this is talking about an emergency stop. The priority is a top priority. It supersedes all of the safety functions. The reset, this will be taken out of the standard because there's requirements for emergency stop resets. So the actuator must be physically released. After the button is released, a manual reset function is carried out by pressing reset button S1 on the operating panel, releasing the emergency stop button or activating the reset button will not initiate any movement. So you've got to reset and then start the machine after the release the button, press a reset, and then press a start button after an emergency stop. For the demand rate, the installation functions 5 days a week, 12 hours a day, and it's expected the stop is checked and activated monthly. The motors are activated every 5 minutes by the standard control system. So this would all be information which will be going into your verification as well. The demand mode, so the entire safety function operates in a high demand. And then there's information again around response time, so it'll be 500 milliseconds. There's interfaces, so connection between subsystems is hardwired, status indication of the emergency stop button and fault alarm is provided on an HMI. Then fault reactions, so it's normally closed. Any open circuit on either channel will result in the activation of the safety function. So if that would mean we're going to detect single channel failures as well, or any damage to the e-stop button. And that might be, so with our e-stops, Pilz e-stops, we have a 3-position contact. So I know many years ago there was issues with contactors falling off the back of e-stop buttons. So if that ever happened, then one of them channels then would open again, and therefore you would be able to detect that that contact had fallen off the back. We've got short circuit detection provided with the use of test pulses. If you were going to use a standard relay, then you would have a opposite polarity on the 2 channels. Both power contactors have monitoring across the normally closed contacts wired in series to the safety relay control system. So failure of the contactors will be detected by the safety system. This is the feedback loop it's talking about. And a detected dangerous failure of either contactor will result in suspension or activation of the safety function. So it will bring everything to a stop and not allow a reset possible. And it states about the operating environment. It's a normal environment, nothing to be considered, and the target performance level was D. So this is kind of this is going to be needed for every safety function moving forward under the requirements of the latest version of the standard in your SRS. As I said previously, there's a bit more information also, or guidance given on how to determine the probability of avoidance. So we're going to look at various factors, which could be the speed at which the hazard arises. Is it possible to escape it? You know, are you trapped, or have you got a lot of room? Practical safety experiences relating to the process. Do you know when you design it? When people understand it, may say, well, this is less likely to happen, or less likely to, or easily avoided. Trained and suitable operators. I mean, this could be anything from, the difference could be where you're maybe working in a test facility where actually the operators are very highly skilled engineers, or where you may be in a logistics center where many of the operators are from an agency and there's a high staff turnover, or something such as that. And also, is it a single man operation, or are there multiple people in the area? So these are all considerations, and they're written in the white column there as factors. And then we've got A, B, and C. So these different factors. So is the machine used by an unskilled or a skilled person? Is the hazard high speed, medium, or low? And then there's a bit more guidance given to that. Spatial ability to not to avoid the hazard, not possible, possible, and we go through it. But there's more and more parts there which you can read in detail. The key part comes to the table at the bottom. If any one of them factors results in a red outcome, so something from column C, you're in P2. If 3 or more result in a amber or a B outcome, you're in P2. Slight ambiguity comes a little bit when you get 2 of Bs and 3 As. Then it's going to depend on the specific hazard, and this might be just that actually that the hazard or the risk is very high. So if it's going to be a really serious injury, you might still want to go down P2. Anything below there, 1 amber or all greens, then you're in P1. I think that's better than it was previously, because it was sort of just left to people to make their own judgment. Also, Annex H looks at the realization of a safety function as a combination of several subsystems. So you can see how it would look on the machine with the door, with a non-contact switch, then the logic device, and then the contactors shutting it down. So multiple safety functions are typically present to reduce machinery risk. But each safety function is realized as a combination of several, and either previously validated subsystems through the subsystem manufacturer, or designs a new subsystem by the machine or the builder. So Pilz components would be essentially validated as the manufacturer. so our sensors and logic devices. And this is how it would be modelled also in Pascal as a system. There's a bit more guidance given. We went into a bit of detail actually on category 2 and how that would operate with the test channel earlier. So there is more information given on that within the standard, but it's basically looking at how that reacts under fault condition and the times at which it can be done. Again, there'll be further details given on how faults and their effects can be assessed. So only consider faults of interfaces for pre-validated subsystems, or fault exclusion as only being possible for certain failures of an element, and fault exclusions shall be justified and documented. So you've got to make sure if you're going to make a fault exclusion to anything, you must document that. They don't always need to be within the same panel. They could be spread across numerous panels. But generally, if you're going to make a fault exclusion, you've got to justify it and be very, very confident of backing that up. Again, there was more information given on the requirements regarding software and the management of functional safety, particularly regarding safety-related application software. And the standard contains the precise specifications on how the software design and validation process would be formulated. And this is going to be dependent upon the performance level. You go through to Annex J for a lot of this information, and it talks about low and full variability software. Full variability software is really for sort of computer programmers where all you can do whatever you want within the software. Generally, within safety systems, you'll be looking at more of a low variability software, that'd be the multi or something, or even pre-configured function blocks and things that will be in your more complex safety PLCs. As we said, the parts of validation, parts of 13.9 part 2 is put in section 10, and it does reiterate that analysis only complements testing. It doesn't replace it. So you may have an idea of that you think your safety system is going to be good when it comes to the validation, but you've still got to test it. You're still going to need a matrix which is showing your switching devices, your output devices, and how they're meant to operate. Again, there's more information actually around the programming of this if you're going to use a logic device and the V model and things such as that. And you review this again, say against your SRS and your FRS. And there's some simple examples on software which have been given. Regarding EMC, there's a new Annex L, which gives you more guidance on the requirements for EMC and how cables need to be run. And there's a checklist and a scoring methodology within the table, which is there and gives you some requirements dependent on your performance level, which you've got to achieve. Where technological measures are not relevant, scores attached to the scoring column can be considered in the comprehensive calculation. Again, zones for this can be located inside or outside the cabinets. Requirements not relevant for single channel subsystems. If you're going to score the PLC, when you're doing that, you're attributing the score for EMC against the PLC, that can only be done once per safety related control system. So there is, like I say, there's a whole table which gives you the guidance on that in Annex L. So that sort of draws us to a close for today. Like I say, we haven't gone too deep into the standard, otherwise we would be here all day. But hopefully it gives you a taste of 13849, what you need to do, how you can achieve a performance level, and I'll identify that. If you want to know any more, we do have some machinery safety training which we offer. So either on functional safety, we also do the TUV Nord certified expert in functional safety. So so that is available as well, which we deliver and get the TUV Nord qualification. We have some of the topics coming up in the webinar schedule this year, or you can go to the Pilz Go to webinar page. It's available on our website, and you can see all the other webinars in which we've previously delivered if you want to get up to speed with any other parts. So thank you everybody for today. Thank you for your time. I hope you found it useful and enjoyed it, and I hope you all have a great weekend. Take care.